Hi. Okay, so this is chapter 7C, the law of large numbers. So we're going to start with just a definition. It applies to independent events only. Okay, applies to independent events only. So consider the theoretical probability, P of A. Sorry, theoretical probability, P of A in a single trial. Okay, so two things. For a large, oops, sorry, I want to make sure you can see all of that. There we go. For a large number of trials, the empirical probability will be close to P of A, meaning if, theoretically flipping a coin is 50-50 heads or tails, then if I flip a coin 100 times, but I get heads 48 times and tails 52 times, well, the more flips we do, the closer to 50-50 we'll actually get. That's what that means. And then, so the larger the number of trials. So if I go from 100 coin tosses to say 1,000 coin tosses, 10,000, so on and so forth, the closer to theoretical that we'll actually get. So the larger the number of trials, the closer the empirical probability should be to the theoretical probability. Perfect. Okay, so here's an example. Roulette, playing roulette. A roulette wheel has actually 38 numbers. 18 are black, 18 are red, and then there's 2 green, 0 and 00. What's the probability of getting a red on any spin? Okay, so let's call that A. So A, what's the probability of red? And then B, if the casino spins the wheel 100,000 times, how many times should you expect a red number? So B is essentially taking the probability, but now since we're running the trial 100,000 times, sorry, let me scoot. Since we're running the trial 100,000 times, it's times that empirical probability. Okay, so probability of red, right? Part over a whole. Over a whole, we know there are 18 red over 38 total, right? So then that gives us 9 over 19, which, let me grab my calculator right here. Here we go. Okay, 9 divided by 19, approximately, let's say 0.47. Approximately 0.47, which is 47%. Okay, so pretty close, theoretical. But now if we play 100,000 times, we're going to multiply that by the theoretical probability. So now I'm going to use the exact number, 9 divided by 19 times 100,000. Right, so that is 47,368.42. 47,368.42 times. Perfect. So that is how many times out of 100,000 we would expect to get red. So this is the idea of large numbers. Basically, you're just saying that the longer you play, the more likely you are to get closer. The more likely you are to win if you're betting on red, or the closer you should get to the theoretical probability. So that leads us right into expected value. So expected value, since you consider two events, each with its own value and probability. Then the expected value is, well, then we have expected value as a formula. It's the value of event one times the probability of event one plus the value of event two times the probability of event two. And then plus the probability, excuse me, the value of event three times the probability of event three. Okay, plus however many events that you have, so to speak. So I would star, highlight, make a note, whatever you need to say, please, I want this on my note card for your future self. So using this as an example, suppose that $1 lottery tickets have the following properties. 1 in 5 to win a free ticket worth $1, 1 in 100 to win $5, 1 in 100,000 to win $1,000, and then 1 in 10 million to win $1 million. What is the expected value of a lottery ticket? Okay, so first, the expected value is that you pay. That's why it's minus $1, right? We have to buy a ticket. So if we're using the, whoops, let me show both on the screen. If we're using the formula, which we are, that's the event value. So that's the dollar we paid times the probability, which is 1, because we bought it. We bought the ticket. It's 100% that we bought the ticket. That's why the probability is 1. So that is -1. And then here's the value, here's the probability. So it's 1 times 1/5. So that is 20 cents. And then $5 times 1 in 100, that is 5 cents. $1,000, right? So at this point, you'd have to buy 1,000 tickets. And 1 in 100,000 wins, right? So that's you buying, excuse me, $1,000 wins 100,000. So one person wins $100,000. Okay, so that gives us 10 cents. And then to win $1,000,000, 1 0 0. Let's see if I can manage how many zeros there are. And then let's see, 1 in 10 million people, or one person out of 10 million wins the $1 million. That is, excuse me, this one was 1 cent. Sorry, I can't mental math. Y'all know that by now. Let me just show you how I'm getting these numbers. So 1 million divided by 10 million. So that is the 10 cents. So the expected value is 10 cents. So if we add all of these up, right, because the equation says add, add, add. So adding all of these together, we get -1 plus 0.2 plus 0.05 plus 0.01 plus 0.1. That is a -64 cents. So we would expect to lose 64 cents. Okay, so the total expected value is negative 64 cents. So what does this mean? Why do we care? Because for every ticket purchased, the buyer can expect to lose, oh, excuse me, 64 cents on average. So if someone buys one ticket per week for a year, remember there's 52 weeks per year. So the yearly expected value would be 52 times the negative 0.64. So negative 0.64 times 52, that is a negative 33.28. Oops, sorry. Don't see any of that, can you? My mistake. So again, the reason being is that even though your value is $1, if you play often enough, the reason why it's not negative 52, because you're expected that every once in a while you probably want a $5 ticket, a $1 ticket, right? So you're expected to win those lower price ones more often. That's why it's not a greater negative, because you are expected, almost theoretically every 5 times to win $1, every 100 times to win $5. So that's why it's not a bigger loss than you would expect. All right, and then last page, we've got more examples. I would like it if you could pause the video after I read, pause the video, work it yourself, and then press play when you're ready to get back into it. But here we go. So you're planning to purchase a painting at an art auction. The cost of the painting is $50,000. You believe that you have a half probability of reselling the painting to a client in New York for $70,000 and a quarter probability of reselling the painting to a client in San Francisco for $80,000. Otherwise, you got to keep it, and you're losing $50,000. So what is the expected value of this $50,000 bid? So notice the hint here, there are 3 relevant events. Because you're buying it, you're potentially selling it for $70,000 at a quarter probability. Oh, excuse me, $70,000 at a half probability, a quarter at $80,000. So those are the 3 that we're interested in. Again, press pause. I want you to try it on your own, and then when you're ready, come back. Okay, you're back. Woohoo! So we have a negative $50,000 times 1 for the event value, and here's the probability of event E, right? So the probability is 1 because it's 100% we bought it. In this scenario, we 100% bought this painting, right? So negative $50,000 in our bank account. But plus the 70K, we could potentially sell it at a half probability or 0.5, right? So this is the event value for event E2. So the second event is that I sell it to the New York person? Yeah. And then 80,000 potentially to the San Francisco person, and it's a 0.25% likely, okay, 0.25. This is the event value, again, times the percent of event 3. Hopefully this makes sense. I wish I could stop and get your questions. But again, it's negative 50,000 because that came from our checkbook or our bank account. And then we add the 70, we add the 80 because these are potential income if we sell to the New York person or the San Francisco person. So I've got negative 50,000. And then plus, I'm going to use double parentheses here. 70,000 times 0.5, because that's a half. Close the parentheses plus double parentheses. I guess I really need double parentheses. 80,000. Making sure I have enough zeros times 0.25. Okay, so the expected value is a $5,000 gain. So here, that's negative 50,000 plus 70,000 divided by a half is 35,000. And 80,000 divided by 4 is 20,000. So 35 plus 20 is 55, minus 50,000 is a positive 5 grand. Perfect. So what does this mean? So we risk 50K, but it's to gain $5,000 profit on average. So basically, we're putting our eggs in the basket that the New York or San Francisco person is going to buy it. Almost done. Just keep with me. Almost done. Just this last definition and an example, and you're done. I am assigning you a quiz to go along with it. Obviously, there's not going to be an in-person worksheet because we're not in person for this. My poor little baby son is sick, so I'm at home with him. Anyways, the gambler's fallacy, the mistaken belief that a streak of bad luck makes a person due for good luck. That's not a thing, right? Luck, not a thing. But it's also called the gambler's ruin, right? Someone is just like, I gotta win soon. I gotta win soon. They keep playing, but they're actually going to lose. Okay. Because that's the expected value, right? Casinos are home field advantage, if you would. All right, so here's a coin toss, another gambling game. You're playing a coin toss game where you win $1 for heads and lose $1 for tails, right? So theoretically 50-50. So after 100 tosses, you have lost 10 because there were 45 heads and 55 tails, right? So it's plus $1 for heads minus $1 for tails. So that is net $10 loss, right? You decide to keep playing because your luck is bound to turn around, right? So you have the gambler's fallacy. After 1,000 coin tosses, there are 480 heads and 520 tails. Does the result agree with what we expect from the law of large numbers? Have you won any money? Well, the first 100 tosses, right? So the 100 tosses, the empirical probability says 45 over 100, which is 45% that you're going to lose on every toss, right? So then for 1,000 tosses, the empirical probability is now 480 over 1,000. So this is 48% of a loss. So we're getting closer to that theoretical probability, right? So getting closer, but we're not 50-50. So this is close to the theoretical probability of 50%. But at this point, you have lost a total of $40. All right, you lost a total of $40 because we have 480 wins for the $1,000, right? We have 480 wins, but 520 losses. So that is a negative $40, right? So we're in the hole $40. So basically, you should have just quit while you were ahead, right? Because that was a difference of $10. You should have just quit when you realized you were losing money. So this is 4 times what you would have lost if you stopped after 100 tosses. Okay, so that's it. That's all that 7C is. The law of large numbers, just expected value, right? Expected value, it goes back to the event value times the probability it's going to happen for the first event, and then start over again. Second event value times that probability. Third event value times the probability it's going to happen, and then plus, however many events you have. That's it. So then there is a quiz I'm going to assign you for 7C. And then when I see you next, we'll move on to 7D. All right, y'all have an awesome day. Bye.